All right, these are the notes for section 3.2, day 2 for pre-calc. We are looking at example 6, which you guys have just read through correctly. Yes? All right. The question is asking if 2,000 grams of this chemical or this element were released at Chernobyl, how many grams are present today? What was the half-life for cesium-137? Did you find that in the reading? 30 years, yes. All right, so after 30 years, it's been cut down to half, yes? Half of the substance is no longer radioactive. Has it been 30 years? It happened in April of 1986. So April of 2017 would put us at how many years? 31. So we're just a little bit under that. How much under? About 3 months. So about a quarter of the year. So let's say our time for this is 30.75. We aren't quite to that 31-year mark. So what would a good estimate be for how much is left? If we start with 2,000, slightly under 1,000, yes? Because the half-life is 30 years, and we've gone just a little bit past one half-life. So it's been cut in half once, and then just slightly more. So our answer should be just under 1,000. Okay, how do we find it? Write a formula. Good answer. Let's write a formula. What do we have? 2,000 times a half. Okay, I'm going to use a t divided by 30. Everybody okay with that? So what are we going to plug in? We're going to put in 30.75 for our t value. Go ahead and grab your calculators and do that. What do we get? 982.821. Might have missed a zero in yours. Okay. 982.821 grams. Now, is that reasonable? Yes, we said we should be just under 1,000. Okay. Second part of the question says if 20 grams is considered to be a safe level, how many years will it take for the levels to reach something that's safe? Now, we've been doing an intersect, yes, for this type of question. And I did mention this week that we are going to learn how to do this algebraically, and by the time we get to the test, you're going to be expected to do that. But we're looking for when does our total amount of 2,000 get cut in half every 30 years? When will we get down to that 20 mark? And students often have a little hard time trying to figure out what kind of window to set for something like this. Let's think about it. After time 0, we had 2,000 grams. After one half-life, we have what? 1,000. After 2 half-lives, we're down to 500. After 3 half-lives, we're down to, thank you. After 4 half-lives, we're down to, okay, 5 would be 62.5. 6 would be 31.25. 7. Have we gotten to the 20 mark by 7? Yes, we've bypassed it just a little bit, right? Now these are half-lives. So 7 half-lives is how many years? 7 times 30, 210 years, yes? So if you made your window big enough to see 210, you know you're going to have hit it. Yes? Okay. What do we get? 199 point. Okay, so about 199 years, and we've only gone almost 31 years so far. So it's going to be quite a while yet before we reach that. Okay, questions on that one? Okay, the big focus for today, that last one was an exponential one. We didn't quite get to it yesterday. Our big focus for today is logistic curves. Do you remember how those look? That S shape, right? We have asymptotes at 0 and C. Yes? We have an inflection point where? Halfway between those? Okay. And it's growing the fastest as you hit that inflection point, and then it starts to slow down again. Okay, so we have this basic model, f of x equals c divided by 1 plus a times b to the x power. We are given some conditions, and they want us to come up with an equation for this. It says the initial height is 5, the limit to growth is 30, and it has to contain the point 315. So let's start with limit to growth. Where would we put the 30 in our equation? That's your c value. Yep. Okay, so we already know that that's got to be a 30. Now, what they've really given us is two ordered pairs. We see this one, right? So we know that's one of the ordered pairs it has to fit. But they said the initial height was 5. What ordered pair would we have for that? Okay, so they're really giving us two values. We can plug in the 0, 5 combination and get one of our variables. Because what happens if we put a 0 in right there for x? Then b to the 0 becomes 1. 1 times a is just a. Yes? So by putting a 0 in, we've eliminated one of our variables here, and we can solve for the a piece. Okay? So that's our first step. We have f of 0, 30 divided by 1 plus a times b to the 0, and it's supposed to equal 5. Okay, and we just said that b to the 0 is 1, 1 times a is just a. So this becomes 30 divided by 1 plus a equaling 5. How would we solve that for a? Okay, you can think of it as a proportion. Pretend there's a 1 under the 5, right? Cross multiply. So we're really multiplying this 1 plus a piece over here to the other side. Now, I have two options. I can distribute the 5 in, or I could do what? I could divide it to the other side. Is it clean to divide it to the other side? Yeah, I don't have any nasty decimals or anything. It's going to work out nice. So if I divide this 5 over here, I get what? So 6 has to be 1 plus a, so a would have to be 5. Okay, so now in our formula, we had 30 as our limit to growth. We just found our a value to be 5 times b to some power. So now the only thing we don't know is b. Okay? Can I use my remaining point to figure that out? Yeah, because this f of x has to be 15 when x is 3. So by plugging a 3 in for my x and a 15 in for my y, now the only thing that I don't know is b. And we can solve this similar to how we just did the other one. All right. So can I multiply the denominator over here to the 15? So 15 times 1 plus 5b cubed equals 30. And again, I can distribute that 15 or divide it over. If I divide it over, 1 plus 5b cubed equals 2. Then what? Subtract the 1, so 5b cubed equals 1. So b cubed equals 1/5. How do we find B? Okay. Okay. Is that equivalent to saying 1/5 to the 1/3 power? All right. Go ahead and give me a decimal for the cube root of 1/5. All right. Now, could I simplify 1/5 to the 1/3 power? 1 to any power is 1. That's not going to change anything. But 5, could I bring this 5 up and say it's to a negative 1/3 power? Okay. I'll explain in a minute why I'm giving you both versions here. So we have found A and we have found B. Let's write our formula. F of x equals, our limit to growth was 30. We had 1 plus 5 times B, 0.585 to the x power. Okay? Next year, when you take calculus, you're going to have a lot of tests where it's a multiple choice versus having a free response type question. Okay? If this was a free response type question, I would accept that as an answer. You've given this the B value out to 3 decimals, that's fine. If it was a multiple choice question and you're looking at the answer choices and it's not one of those, or that's not one of my answer choices, it's possible that they used a different version. Okay, so how could we clean it up if we used B to the if we used 5 to the negative 1/3? What would that look like? What'd you say? Okay, multiplying the x in makes this negative x over 3. Okay. Try that again. Yes? Now, we have a base of 5 in 2 different places. We have 5 to the first, and we have 5 to the negative x over 3. Can we combine that? What would we do with our powers to combine that? Base to a power times the same base to a power. You add them. All right, so it would look like this. 30 over 1 plus 5. And now we need to add negative x over 3 plus 1. So that's another version that's equivalent, but that might be the one you're given. Okay, so just make sure that you understand the algebra involved in simplifying that. Okay. All right, grab your calculators. We're going to do some regression equations. All right, example 6 says use the 1900 to 2000 data in table 3.9 and an exponential regression to predict the U.S. population for 2007 and compare the result with the listed value for 2007. Now be careful here because in our table of values, and some of you are already starting to type it in, hang on a sec. In our table of values, we have years from 1900 to 2007. But they said just use the data from 1900 to 2000 to come up with a model. So the only reason they're giving us this 2007 data is so that we can compare, try that again, we can compare our answer to what the actual value was for 2007. Okay? What did they say for time? T stands for the years after 1900. So what are we going to put in for this first year? 0. And then 10, 20, etc. Yes? Okay, I'm going to pause the recording here. Go ahead and enter the years as list 1 and the population as list 2. All right, so we have our list 1 contains our years starting with year 0. Population is in list 2. And it says to do an exponential regression. So you are going to go to PreCalc, scroll down to find exponential regression. It's number 0 on my menu. Okay. And then years has a list 1, list 2. And then you can store it doing variables, y variables, function, and the first equation, y1. Okay, always be really careful to look at what equation they set up. Sometimes their variables are in different spots than we're used to seeing. Okay, we just want to make sure you put it in correctly. It says y equals ab to the x power. And what did they give us for an a value? 80.551. And b was, okay, and I'm going to go ahead and put that out to a few more decimals, and then we'll just give our final answer as 3 decimals. And we want to raise that to the x power, or the t power, sorry. Okay, so we've got our model. What does our r value say on the calculator? R is 0.9975. Does that mean we have a good fit? Yes. It means the data that we have, if we actually graphed it and looked at it, would be really nicely fitting this curve that they've given us. Okay. The question now says compare the result with the listed value for 2007. So the actual data for 2007 says we were supposed to have 301.6 million people. Let's see what we get based on our model. So what is the value in 2007? What would my year be? Okay, so we're going to put 107 in for time. What do we get? Point what? Okay. So a little bit over 317 million people. But what did the actual data say? 301.6 million. Yes? So we're a little high, which means if we look at our graph, all right, we've got our curve here. This is the actual data point, right? But our curve is showing us being higher. Okay, how much higher are we? What would be 317.128 minus 301.6? Okay, so we're about 15.5 too high. Is that a lot? We're talking millions, right? So we're 15 million over what we're supposed to get. Is that a big deal? Well, 15 million compared to 300 million, not huge, but it still is a little bit off. If you wanted to figure out the percent error that you had, you can take that 15.5 and compare it to 301.6, what you're supposed to get. What do you get as a percent for that? Okay, so we're about 5% error. Now, is that too big of an error? It kind of depends on what you want to do with this data. All right, maybe 5% off isn't too bad. Okay, so again, the blue dot here in this last graph is the actual value we got from our model, the 317 million, whereas the red is the 301 million. Okay, Our second one is going to be a logistic curve. And we've talked about logistic growth being what happens when things can't grow continuously at a faster and faster rate. Okay, they start to slow down. The limit to growth, we've had a few different terms for it. Limit to growth, carrying capacity. Now they're saying, refer to it as the maximum sustainable population, right? The biggest it can get. It says, use the data in our table and a logistic regression to predict the maximum sustainable populations for Florida and Pennsylvania. In other words, we're trying to find those limits to growth. Okay. It says to graph the logistic models and interpret their significance. They're telling us to use F of t and P of t for the populations in millions for Florida and Pennsylvania. T years after 1800. So in our table of values, or in our T-chart here, what are we going to use for our year? This would be 100, 110, 120, etc. They haven't given us any restrictions in terms of how much of the table to use, so we're going to use the whole thing. So go ahead and enter. We've got 3 different lists. So you can use lists 3, 4, and 5 if you want. You can clear out your old data and enter this as lists 1, 2, and 3. I'm going to pause the video and let me know when you're ready. Okay, so we are going to find a logistic regression. We're going to do this twice, once with the Florida data, once with the Pennsylvania data. Okay, so go back into your stat calc, scroll down, and it should say logistic. Everybody finding it? Okay, so we're going to do a logistic one. Tell it which lists to use. So if you did list 3, 4, and 5, you're using list 3 and 4. If you did 1, 2, and 3, you're using 1 and 2. Okay. Did anybody get the equation yet? Okay. Mine's being slow here today. So this is Florida's. And we have what for our carrying capacity? What's our C value? I'm not. Maybe I got the wrong number. It should be 28.021. Yes? Okay. Now, here's an example where you have to watch where to put the numbers, right? They give you the formula at the top of your screen. All right, it says y equals C when C is 28.021 divided by 1 plus our A value is 9018.633. And then what else is next in that formula? Yeah, they're giving a base of e to a power. Okay, so we need e to the negative 0.047 x or t. Yes? All right, go ahead and redo that same thing, but for the Pennsylvania population. So make sure you tell it which lists to use. got a 5 there instead of 0.5.
Oh my God.
Okay, what are we getting? I'm getting 12.579 for C. Are we good or not? Okay. No, Kaya's not good? Okay, so our equation is 12.579 divided by 1 plus 29e to the negative 0.034t. Yes? Okay. Now, the question asked us to find the maximum sustainable population, or that carrying capacity. So for Florida, the maximum was 28.021 million. And for Pennsylvania, our maximum was 12.579 million. Okay. And then it says to graph it and interpret it. I've gone ahead and given you the graphs down here. Pennsylvania is in red. How do I know that? Because if I look at my data for Pennsylvania, I have starting point at 6.3, which is higher than my data for Florida. Yes? So this is going to be the top graph. If you compare the data between Florida and Pennsylvania, in Pennsylvania, you're starting at 6 million and going up to 12 million. And at the beginning, those first couple of years, it was going up by about 1 million each year. But then towards the end, look what happens. You're at 11.8, 11.9, 11.9, 12.3. It's slowed down. Yes? So when we think about our logistic curve, Pennsylvania is already kind of getting to the end. Its limit to growth is 12.579 million, and we're already at 12.3. Okay, so we're close to leveling off there at our capacity. Whereas Florida has a limit of 28 million, and we're only at 16 right now. So we're still growing. We haven't reached that leveling off point. Does that make sense? All right. Couple other logistic models. It says in example 3, the bacteria cannot continue to grow exponentially forever because they cannot grow beyond the confines of the petri dish. In example 7, though Florida's population is booming now, it will eventually level off, just as Pennsylvania's has done. Sunflowers and many other plants grow to a natural height following a logistic pattern. Chemical acid-base titration curves are logistic. Yeast cultures grow logistically. Contagious diseases and rumors spread according to logistic models. So this example says we have a high school with 1,200 students. Carol, Bob, Ted, and Alice start a rumor which spreads logistically so that our equation S of t equals 1,200 divided by 1 plus 39e to the negative 0.9t models the situation. T stands for the end of day t. Okay? So if we had a t value of 2, it means the end of day 2. How many students have heard the rumor by the end of day 0? What are we going to do? Plug a 0 in. Yep. All right. So S of 0. We've got 1,200. What happens in the denominator? We end up taking e to a 0 power, which is 1. 1 times 39 is 39. 39 plus the other one is 40. So we end up with 1,200 divided by 40. So we have about 30 kids who know the rumor after day 0. Okay. Second question says, how long does it take for 1,000 students to hear the rumor? What are we looking for? Okay. So we want our answer to be 1,000. Our formula says it's 1,200 over 1 plus 39e to the negative 0.9t. So we're going to do an intersect. Go ahead and try that. What do we get? Anybody? These calculators are just slow today. 5.859. So we get to having 1,000 people hearing the rumor towards the end of day. Careful here. Yeah, because if T was exactly 5, it said that stands for the end of day 5, right? So we're almost to the end of day 6. All right, and if you graphed it, you'd be able to see that nice logistic curve. Okay. All right, I'm going to give you one to try. I'm going to pause the recording, have you guys try this, and we'll come back periodically to check your answers. Okay? All right, let's check our first couple answers here. We should have had at the end of day 0 about 2 students infected, the end of day 3 about 3 students, and by day 10 about 6 students. Yes? And remember, this is logistic growth, so it's going to start slowly and then start growing faster and faster till it hits that inflection point and then start slowing down again. Okay? After how many days will 10 students have been infected? So we look for an intersection between 10 and our equation. And we ended up with a time of what? 15, what was it, 0.177, something like that, days? Okay. The third question says, after how many days is the flu spreading at its fastest rate? When does that happen? At the inflection point, good. So what would our inflection point value be for Y? 1100. So we're looking for an intersection of 1100 with our equation. All right. Did anybody find that point? Okay. So we have a horizontal asymptote up here at 2200. We have this nice logistic curve, and we're looking for at 1100. And you said it was about 69 days? Okay. All right, part D. It says, according to the model, after how many days will the entire student population become infected?
146-ish.
Will we ever get to the entire population being infected?
No.
According to the model, we have a horizontal asymptote at 2200, right? So we're getting really, really close to that, but we don't actually get to it. So the answer here is actually never. It approaches the horizontal asymptote of y equals 2200, but does not reach it. All right, and then the last part. Did you have time to get this one done? Some of you? Okay. It says, if the school policy is to shut down the school if at least 5% of the student population is infected, after how many days would that happen? So we have to figure out 5% of our total population, right? Which is how much? 110? Okay. So they're going to shut down the school if 110 kids have the flu? So we need to do an intersection with 110 and our model. All right, and it happens when? 39.623 days. So about day 40, they would shut the school down. Questions on that?
Some of them would be coming back.
No, it does. The initial ones wouldn't still be sick. You're right. Okay, day 2. We're doing 23 to 25, 27, 28, 39, 37 to 39, 41 to 43, 45 to 47, 50, and 55 to 56.